In lesson 6, we're going to learn a new theorem called the rational root theorem. And this theorem is going to be helpful when solving higher degreed polynomial equations. So what the theorem says is that for polynomials with integer, so meaning negative or positive whole numbers, coefficients, every rational zero has the form P over Q, where P and Q have no common factors other than 1, and P is a factor of the constant term, meaning the number at the end, and Q is a factor of the leading coefficient. So what this means is this theorem is going to be used as a way to help us find the solutions to an equation that's set equal to 0. So the reason, if you look in here, we say for polynomials with integer coefficients, every rational zero. So when we say every rational zero, what we mean are all of the solutions. So any rational solutions when we set this equation equal to 0 is going to be of this form, P over Q, meaning P is one of the factors of the constant term and Q is one of the factors of the leading coefficient. So rational zero means rational solutions to this equation. And remember, rational numbers are just numbers that are either fractions, whole numbers, integers, decimals that can be written as fractions, decimals that end, decimals with patterns, all of those. So any of our answers that are rational numbers are going to be of this form, is basically what it's saying. And the reason why we have this theorem, if you look at this first example, and if you want to solve this, and let's say you can't solve it by factoring. So what you can do is you have to basically figure out what one of the factors are. So if you know what one of the factors is, then what you can do is you can divide by that factor using synthetic division, and then from there, once you can factor, you will begin to factor. So this example, if you look at it as, okay, let's look to see if we can factor by grouping, and even if you split it down the middle, you won't be able to pull out a GCF out of this right side or out of the left side. The left side you could pull out an x squared, but it's not going to give you the 8x plus 3. So since you can't factor anything out of this side here, it's not factorable. So this expression, or this equation, is not factorable, which means we need this other method. So what we do is we use the rational root theorem to find the zeros. And remember that the zeros are just the solutions to that equation set equal to 0. So anytime we say rational zeros, these are just the solutions to the equation set equal to 0. That's why they're called the zeros. So what we're going to do is we first have to take this expression, or this equation. So let me just rewrite it down here. So I have 2x to the third plus 3x squared minus 8x plus 3 equals 0. First thing you have to do is identify the p and the q values. P is always the constant term, so this is the p, and q is always the leading coefficient. So what we do is we have to figure out all of the factors of p, all of the factors of q. So the factors of p, well, we have 3 for p. So the only two numbers that are going to work are going to be 1 and 3. But because you have to consider negatives, you have plus or and minus 1, plus or minus 3. And then we look at the factors of q. So this is q. So the only numbers that are going to multiply to q, or to multiply to 2, are going to be 1 and 2. But again, we're going to have plus or minus because you can have positive or negative numbers to get you to 2. So then what this theorem says is that any possible root, so possible solutions or possible zeros to this equation, have to be of the form of p over q, which means plus or minus 1, plus or minus 3 over these other factors. So possible solutions or possible zeros to this equation are in the form p over q, which really means we have plus or minus 1 for p, we have plus or minus 3 for p. For q, we have plus or minus 1, and we have plus or minus 2. So I'm just kind of like listing out the factors. And these are just possible solutions. It doesn't mean that they're going to work, all of them. It just means that these are basically eliminating all the numbers from negative infinity to positive infinity down to just a couple of numbers. So when we look at this equation, I don't know what I can divide by, so that's why I'm going through this whole process to figure out, well, what is a possible solution, and then I can divide by that, and then hopefully get something that's factorable. So since I don't know the number, I use these possible zeros, and what this really means is the possible zeros then are the numbers basically you take and you divide these ones. So we would have plus or minus 1 divided by 1, which is 1. Plus or minus 3 divided by 1 would be plus or minus 3. And then we have these factors when you divide them by 2. So we would have plus or minus 1 divided by 2 and plus or minus 3 divided by 2. So those are all of the different combinations. So that means 1, 3, 1/2, 3/2, and then the negatives of all of those are the only possible zeros to this equation. So these are the only possible numbers that I could divide by or do the opposite signs as factors, and they would work in this, they would be factors of this equation. So what I'm going to do is now you just kind of have to pick. So we've eliminated it down from all real numbers down to 8 choices, 4 positives and 4 negatives. So basically what I usually do is I pick like 1 or -1 to start and see if it works. So let's say I pick 1 and I say, okay, I'm going to take my equation up here and I'm going to divide that by x minus 1. I'm going to see if basically x minus 1 is a factor, which means 1 would be a 0 or a solution. So I'm going to go ahead, I'm going to use synthetic division. So I'm going to take this and I'm going to rewrite it with my coefficient. So I have 2, 3, -8, 3. And I'm setting this up for synthetic division. And basically what I'm going to do is I'm going to test, I just pick one, so let's say I test positive 1. So that means I'm going to divide everything by positive 1. And I chose that because it was one of my possible zeros. So I'm going to carry down the 2. So 2 times 1. So again, synthetic division, multiply diagonally, add vertically. 2 times 1 gives me 2. 3 plus 2 gives me 5. Multiply, we get 5. Add, we get -3. Multiply, we get -3. Add, we get 0. So what that means is I got a remainder of 0. So my remainder, when 2x, so whatever our original was, so 2x to the third plus 3x squared minus 8x plus 3 was divided by x minus 1. Remember, you always do opposite signs, so the factor is x minus 1. The 0 is 1, so I divide by the 0, but then when we say what we're actually, like in the synthetic division, we use the 0, but we're really dividing by the factor. So when the remainder, when I divide this expression by x minus 1 is 0, so what that means is, so x equals 1 is a 0, or solution, means the same thing, of the equation. So that's what that means. Now, let's say you go through this process and you don't get a remainder of 0. Let's say you get a different remainder. So let me just show you. What if I would have done this where I said, okay, I want to test -1. I start with -1. So I want to see if x equals -1 is a 0, meaning x plus 1 is a factor. So I'm going to basically start it off the same way. I'm going to have the 2, 3, -8, and 3. And then I'm just going to go ahead. So bring down the 2, multiply diagonally, we get -2, add vertically, we get 1, multiply diagonally, we get -1, add vertically, -9, multiply, we get 9, add them, we get 12. So since my remainder is not 0, that means x equals -1 is not a solution. And that means that x plus 1 is not a factor. Or what that also means is if you take and you have 2x to the third plus 3x squared minus 8x plus 3 divided by x plus 1, you're going to get out a remainder. It's not going to be a factor. It doesn't come out nice. So what we need to do now is basically if you test something and you get out a remainder that's not equal to 0, then basically you just kind of throw that out. You just kind of reject that scenario. So remember, the rational root theorem gives you possible roots. So basically we know that +1 is a root and -1 is not a root. So what I'm going to do is I'm going to continue using this piece over here where when I tested 1 it worked. So what that means is so far I know that 2x to the third plus 3x squared minus 8x plus 3 equals 0, my original equation, can be rewritten as my answer from this division. So my answer from this was 2, so I'm just taking my coefficients. So 2x squared, because remember it's always one less degree if you're dividing by a linear term, plus 5x minus 3. So that means this equation that I started with is the same thing as saying x minus 1 times what I got out, 2x squared plus 5x minus 3. So remember, if you are dividing by 1, that means the factor is x minus 1. And the 0 is x equals 1. So this is always the 0. So when you go to write your factors, x minus 1 is what should go there. It should always be the opposite sign. So that factor times what my answer is gets me the original. That's the whole division process. And then at this step, now that you have just a degree 2 polynomial left, you want to see if you can factor that so that you don't have to keep doing synthetic division. Otherwise, you could test another one of those possible roots from up top, and you could see if it's a factor of this, or just, or just go back to the old method of just factoring. So what I'm going to do is I'm going to do the factor by grouping method. So remember, we multiply these two numbers, 2 times -3. So we get -6, and we're looking for numbers that multiply to -6, but then add to 5x. So that would have to be, if we're trying to multiply to -6 but add to 5, we're going to have to use 6 and -1. So what I'm going to do is I'm going to carry down this x minus 1. I'm going to carry down the 2x squared, and I'm going to rewrite the 5x. So I'm going to rewrite it as plus 6x minus 1x minus 3. Carry down that equals 0. So I have x minus 1. And I'm just going to go ahead now and I'm going to split it, factor by grouping. So I'm going to be able to pull out a 2x. So I have an x plus 3 left. And then here I'm going to be able to pull out a minus 1. So I have x plus 3 left. And then I'm just carrying down the x minus 1. And now I'm going to factor this x plus 3 out. So x plus 3. And I'm left with here a 2x. I'm left with here a minus 1 equals 0. So these are the factors. So if you look, these are the factors, and our roots are going to be the opposite signs of these. So basically what you're going to do is you're going to set them equal to 0. Because you're trying to find the zeros or the roots or the solutions, which means set them equal to 0 and solve them. So this one's x equals 1, x equals -3. And this one would be 2x equals 1. Divide everything by 2, you get 1/2. And if you go back up top, so here are my 3 answers. So I have all 3 of these as answers to this original equation, 1, -3, and 1/2. And if you look back up here at our possible zeros or possible solutions, we have all of those listed. We have the 1 listed, we have the -3 listed, and we have the positive 1/2. So remember, these are called possible zeros, meaning it's just kind of reducing our choices, because otherwise you don't know where to start. So this theorem is just giving us, well, here's a smaller list of numbers that could work. And then in the end, in this case, just 3 numbers work because we started with a degree 3 polynomial. The exponent was 3, which means I had to have 3 answers. So my 3 answers are always going to be in this list of possible zeros. So you test some until you get a remainder of 0, and then from there, you want to just try to factor what's left after you divided by that first 0, or that first factor, and then you just have to set each piece equal to 0 and solve. So let's do one more example just to get you familiar with the process. So let's go ahead and look at the next one. So now we have a degree 4, so since the highest exponent is 4, I'm expecting 4 solutions, or 4 zeros. So remember, solutions, zeros, and roots all mean the same thing. So first thing you want to do is you want to use the rational root theorem. So I'm going to follow these 4 steps here, but I'm not going to really label them, but it's the same process I went through last time. You always got to find the possible zeros first. So you look for the P and you look for the Q. So P is always a number in the end, Q is always a number in the front. So Q is 1. So P, or the factors of P, is what you're going to look at first. So the factors of -6, so P equals -6. So the factors of P, you're going to have numbers that multiply to 6. So plus or minus 1 and 6 would work. I'm just going to go in order, 2 and 3. And then I'm just going to make sure I get that 6 in there. And then for the factors of Q, Numbers that multiply to 1 is just going to be 1. So then your possible zeros, using the rational root theorem, are in the form P over Q, or the factors of P over the factors of Q. So it's the factors of P divided by the factors of Q. So basically, the possible zeros are just going to be all of these numbers divided by 1. So really, any of those numbers divided by 1 is just going to be those numbers. So whenever your leading coefficient is 1, it makes it easier because there's not going to be as many choices. So there are my choices for possible zeros. And again, you kind of just have to pick one and hope that the one that you choose works out to give you a remainder of 0. Otherwise, you might choose a couple of them and you keep getting remainders. You just have to keep going. You just have to keep testing any of these zeros until you get a remainder of 0, and then see what you're left with and see if you can factor it from there. Otherwise, if you can't factor it, you just have to keep going. Like, you just have to find another 0 and divide that 0 by whatever you're left with. So I'm going to start with, let's say I start with 1. 1's usually a good choice to start with. So if I take my original polynomial and I just write down all the coefficients, so I'm going to test 1 first as a 0. So I have my original polynomial, my coefficient 1, -1, 1, -3, and -6. Make sure when you're doing synthetic division that you're writing your exponent or your coefficients so that you're not missing any terms. So like your exponents need to be in decreasing order. Your polynomial needs to be in standard form. So like if I didn't have an x squared, I'd have to put a 0 in there where x squared is supposed to be. So just make sure you remember that. So I'm going to go ahead and I'm going to test 1, which means I'm dividing by 1. So I carry down 1. Multiply these, we get 0. Multiply 0, add 1, multiply 1, add -2, multiply, we get -2, add, we get -8. So this is just to show you that, okay, I tried 1, I didn't get a remainder of 0, so this means that the remainder does not equal 0, and this means that x equals 1 is not a solution. And also that x minus 1 is not a factor, which we learned last time with the factor theorem. So let's try another one. Let's test -1. So the setup's going to be the same. I'm just going to be dividing by a negative, so you can just kind of copy these same numbers. They're just the coefficients of the original. And then you carry down. So we carry down 1, we get -1. Add them, -2. Multiply, we get 2. Add, we get 3. Multiply, we get -3. Add, we get -6. Multiply, we get +6, which is good because we get a remainder of 0. So again, since the remainder equals 0, this means that x equals -1 is a solution, and x plus 1 is a factor. So we want to look at what our answer is from the synthetic division. And if you remember, we started with a degree 4 polynomial. So my answer is going to be a degree 3. So these are going to be my coefficients of my degree 3. And they're going to just go in decreasing order. So we have 3x, and then my constant is -6. So that is what's left after I divided my polynomial. So my original polynomial was x to the 4th minus x to the 3rd plus x squared. minus 3x minus 6 equals 0. That's my original equation. So then what I just came up with is that when I factor, or when I divide this by x plus 1, remember that x minus 1 is the 0, x plus 1 is the factor. So what we just did is we divided our polynomial by x plus 1, which means I was left with this answer. So that means x plus 1 times my answer is going to be equal to the original. So these are my factors, and then I want to keep going. So basically now I look at what was left, which is a degree 3. If this degree 3 doesn't factor, then I have to go through the whole process of testing some of those possible roots or possible zeros into this, divide until I get a remainder of 0, and then that's my factor. You can always do that, but if you can factor it, you might as well just go with the factoring route. I think it's easier. Keep in mind that if these are possible zeros of the degree 4 polynomial, then that means they're also going to be zeros of this polynomial that's left, since they have to be zeros of the entire thing, and these two things are equivalent. So now what I'm going to do, I notice that this is 4 terms, and I notice that there's a GCF in the first 2 terms. There's also a GCF in the last 2 terms. So that's a good indication that I'm going to be able to do factor by grouping. So I'm going to keep the x plus 1, and I'm going to take the GCF out of the first piece, which is x squared. And then I'm going to take the GCF out of the second piece, which is 3. So I get x minus 2 left. And then I'm going to be able to take out the x minus 2. So it's going to be x plus 1, x minus 2, and then it's going to be x squared plus 3 equals 0. And now you can't factor this x squared plus 3 any further, so we can go ahead and we can set each piece equal to 0. So we split it all. So we get x equals negative 1, x equals 2, and we get x squared equals negative 3. Square root both sides, and we get x equals plus or minus. I have a negative under square root, which means it's going to be I square root of 3. So here are your 3 solutions. And if you notice, you have negative 1, 2, and then you have this plus or minus I radical 3. The plus or minus I radical 3 is not going to be found using the rational root theorem. Like, it's not going to be one of your possible zeros that we originally listed. Because if you remember back in the theorem, it says that the rational zeros are in this form. And whenever you have a complex number, that's not a rational number. Same with any square roots, like of numbers that aren't perfect squares. So like radical 2, radical 3. Those are not going to be listed here. So just be aware that these possible zeros are just possible rational zeros. So your rational numbers, though, will always be listed here. So if you look, our 2 answers were negative 1, which was listed, and positive 2. Those are rational numbers, so those are listed. But the complex numbers, or the imaginary numbers, or the irrational numbers won't be listed. So just keep that in mind. So your 4 answers, then, you should have 4 answers, are these numbers here, and your factors are back up top here. So that's it for that one.